So today in Mathletes after school, that would have been at about 3:14 p.m. on Tuesday, January 4th, 2022, we observed Whale Day, which is, of course, the birthday of one of our greatest members, Eric Shawn, who was really interested in whales, currently studying physics in a PhD program in Southern California. But in honor of Eric, one of our greatest of all time, someone that belongs on the Mount Rushmore of Franklin Mathletes, I wrote a problem involving a whale. And in this case, I wrote a problem involving a whale that includes one of my favorite sort of, I want to call it like a problem-solving trope, which is the restricted mammal problem, which in this case means that you take some sort of mammal, be it a dog like it was in last year's steeplechase, or in this particular case, a whale, and you attach a leash to it. And you try to restrict its movement so that way you can kind of see what sorts of geometric shapes or what sort of access it has geometrically. So in those problems, typically you're looking to figure out how much or the maximum volume or area, depending on whether you're in 2 or 3 dimensions, that mammal can actually reach. And in this case, that's no different. So I want to actually present the solution to this problem and talk through what I did in order to make it approachable, talk through some of the interesting geometry that pops up. I think you'll see that there's nothing super advanced here, but at the same time, there's a lot of pieces, and it's a little nitty-gritty for sure. And there are a couple concepts that might be new to you if you haven't yet reached maybe trigonometry. So with all that said, let's jump into what we're calling the Whale Day dilemma. So Moo the whale lives in a band-aid-shaped tank, comprised of a rectangle and 2 semicircles as shown. You can see that tank down below. The radius of each semicircle is 20 yards, while the full horizontal length of the tank is 340 yards. Now I've marked that on here. It wasn't originally marked that way if you were in Mathletes today, so you didn't have that on your document, but now you know. The one thing I do want to add, though, just based on this information here, is the fact that the radius of each semicircle is 20 yards. I think that's a pretty valuable thing to mark just because that allows us to get a little bit of extra information. So from there to there, that's going to be 20. I'll assume all measurements are in yards here, just so that it's clear what's happening. And since each semicircle has the exact same measurement of 20 yards for its radius, that actually helps us identify a key dimension of this picture right off the bat. So in fact, I want to take care of that right now and make sure that we have it marked. So I'm going to mark off sort of the ends of those semicircles right there. Keep in mind, of course, my diagram isn't drawn to scale, so it's made really briefly. But since the entire thing is 340 yards, and we have 20 and 20 is 40 marked off by the semicircles, we can actually point out that this rectangle in the middle is 300 yards long. Now, that doesn't mean that we're going to need that information. I just wanted to make it clear so that way the picture makes a little bit of sense with the description I put in there. I don't think I'm the best describer of geometric situation, so we're clear though. Now, Moo resents his life in captivity, naturally. Maybe he watched Blackfish or something, and keeps trying to ram the far side of his tank because, of course, Moo the whale isn't leashed just yet. This frustrates his keepers, so they cruelly attach a 100-yard leash at the furthest edge of the left semicircle. And you can see that attachment happening right here. So there is Moo's attachment. The blue line right there isn't just a hockey term. That is the leash on Moo, and there is Moo the whale, which also happens to double as Eric's autograph. But beside the point. So our question is, based on this information, what percentage of the tank, and what percentage of the tank's area, I guess same thing, can Moo the whale reach while leashed? And, of course, we're going to round to the nearest whole percent just so that our final answer looks nice. You don't want some sort of awkward decimally thing when you're concluding at the end. So we are going to attach this problem. Before we do, we're going to attack this problem. Before we do, we need to sort of get our mind around what sort of movement Moo the whale actually has access to here. Like if we don't have some command of what that geometry even looks like, we have no hope of actually finding the area that we need. And that is going to be our goal, of course. We're going to find the area Moo can reach, and then we're going to divide by the area of the entire piece. Now, I'm going to save the area of the entire piece for the end just because it's the simplest part, so I just want to kind of save that at the end. But you might be different than I am, and you might want to go that route. So let's think about this for a second. And I'm going to admit that this picture may not be perfect, even though it does have the whale in it. So I'm going to enlist the help a little bit of Desmos. So basically, that's not Desmos. That's Desmos. So this is a 2-scale rendering of Moo the whale's tank. And in truth, I could probably stretch this. Like if you're looking at it going, oh, why don't you zoom in a little bit? Well, I want it to look like semicircles at the end. So this is 2-scale. So at least we can look at it. So now it's important to note, though, that Moo only has a 100-yard leash, Whereas this whole thing stretches, we said in the middle, 300 yards. So Mumu's clearly not going to be able to reach the other side. Now, I might argue with his keepers. Can he still ram his head against the wall on the sides or in the back? Yeah, he can. So you haven't really done anything. You're still cruel and you're bad at your jobs. But beside the point, we can look at this picture and start to think about how far Mumu can move. In a sense, we want to figure out, like, whereabouts can he head that's the furthest away from his point of attachment, right here. And I've called it in this coordinate system negative 20, 0, but it's really up to you. You don't have to call it negative 20, 0. You could have started at 0, 0. So from here, what I want to do first is I want to think about his horizontal movement. So looking at this picture, of course, with a 100-yard leash, Mumu can reach lots of places. There will be some slack in that leash, but he can reach all over the place on here. What he can do, though, is the furthest he can get is when his leash is completely made into a straight line, meaning he's stretched it as far as possible. And what that means is that he can extend from here in a line 100 units away on the diagonal. And that line would look something like this. So there is his leash stretched all the way out. Likewise, Mumu could also go downward and do the same thing. And of course, that doesn't mean that he can't hit here. He can hit this region as well. Don't get me wrong. He can hit that region as well. But basically, he can stretch as far as that, and any area included in there would count. Likewise, he can also stretch as far as this in the opposite direction. It's symmetrical. So in fact, you could probably boil this entire picture down to just the upper half and then do some doubling work. But actually, you probably could just do the upper half. But we'll stick with the classic. So there's that stretch. So good news here, he can hit everything in this rectangle and semicircle. So that's a good stuff. The difficulty is thinking about that last little bit. What can he do in the middle? How far can he stretch? In your mind, you might intuitively think that he can only stretch in a straight line down right there. In fact, I'm going to zoom this in because we don't need to be that far out anymore. You can think that he can only stretch in a straight line right down there. But in fact, that's not true. Because his leash is 100, it actually stretches a little further along than it does right there. Because the full 100 is the hypotenuse, that's the longest side of this triangle. But as we move downward, he's actually going to be able to travel out a little bit. And I have that modeled as well. So now this is a little hard to tell because I've drawn it to scale, but in reality what we have is a little arc of a circle right there. And it's a circle not of radius 20, like the semicircles on the ends of the tank that Mumu's swimming in, but it's a semicircle, or a circle, not a semicircle, of radius 100, because the leash is stretched out all the way. And I might point out that if you think about this, if Mumu starts at negative 20, 0 and can stretch as far as what looks like 80, 0, that's 100 units. So his leash is stretched at its fullest right there. So basically his leash at the edges produces a straight line, and then as he pulls it and keeps it taut, no slack in that leash, so it's a straight line all the way around, he ends up creating a small circular arc. And that represents or kind of bounds the end of his motion. That's as far as Mumu the whale can go. So if we're trying to actually figure out exactly how much area Mumu can hit, our area is going to be this section right in here. And you know what? I'm going to even go into here. Let's delete that really quick. So right in here, the area that Mumu can reach is all of this. So Mumu can get to that whole section. So our job is to figure out how do we find the area of that section so that then we can divide it by the area of the entire tank and figure out the percentage. Maybe this is to get some sort of compliance thing, but again, watch Blackfish. You won't want any orca to be stuck in any tank. So from here, this is what we're trying to figure out. So hopefully that helps a little bit with the geometry. The good news is, of course, we have a good command of the problem now. The bad news is that it's still going to be somewhat difficult to kind of work our way through. And in fact, I think part of that challenge is because we have two separate options that we can use in order to attack this problem. So let's look at those two options really fast. So let's first get two of these pieces to look at. I want to present to you the two solution approaches that we can take to figure out the geometric area of where it is that Mumu can go. So first of all, the first approach, which I think is the one that most students today sort of like latched onto really fast, might be wrong, but I felt like this happened a lot, was to use what we're going to call the sector. It's the formal name for it. The sector is this shape right here. It is effectively a slice of pizza. So in a sense, we could find the area of that thing which once again is called a sector, that is the formal name for it, It's like one slice out of a circle, and it starts at the center and extends out and subtends or intersects the arc that's out there. So you would find the area of the sector, which we'll talk about the approach to finding in just a few minutes. And then from there, well, this is sort of the downside of using what otherwise might seem like a natural method. If you find that, Moo can also find his way into all of these regions. Now again, there's symmetry, but those regions are kind of hard to find because look at the shape. It's some sort of like part of a circle with like a triangle pulled out of it and then another triangle, which again, maybe not that bad. You might be comfortable doing that, especially with the coordinate system that I created here. But at the same time, I don't think that necessarily like cleans up the process a little bit or as best as it could. So instead, I'm going to show you the approach that I took, which I think is sort of a second approach. It wasn't the first one I went for. I also went for that one. But at the same time, I think this approach will work really nicely, as well as unveil some really interesting mathematics that's happening here. So that approach is to do this. First, let's get some bright colors here. First thing I'm going to do is I'm going to figure out the area of this semicircle. So that's going to be my first bit. Why? Because it's easy to find the area of the semicircle. That's it. That's my entire rationale. Second, I'm going to find, and this one's a little bit tougher to see. It might take a second to catch. That's why I'm going to try to straighten this line out a little bit. The second thing that I want to find is the area of this rectangle. So in fact, let's mark these pieces. We're going to do semicircle. And then second, we're going to add the area of that rectangle. Now, the good news is we can quickly find some of these elements of this rectangle, which, by the way, like the height of that rectangle is going to be very easy to find using the information about the semicircle, but we can find that area of the rectangle. The problem is it leaves off one final section, and that section is a bit of a doozy to calculate the area of. And that section I'm talking about is this bit in pink over here. This is called the segment of a circle, and we would need to find the area of that segment. Now, with that said, we could get some really good approximations just by sort of ignoring the segment a little bit. I think we could actually do fairly well, or including it and overcounting it. Like, there's lots of ways that you could actually sort of work around this and get a good estimation of the answer. But if we want to find it exactly, again, using my approach that we're going to use here, you would need to find the area of each of these three. As I said before, though, semicircle's easy. Rectangular is going to be pretty easy. The segment is going to be the spot where, we're going to have to do a little bit of work. It's going to be a little bit more challenging. But that is the approach that I'm going to take. Maybe non-traditional, but I think it unveils and reveals some really good mathematics. So with that said, let's go attack this problem on the next page and start to take a look at the geometry here. So there is our section. I want to go about, of course, first labeling everything as best I can, so that way we can start to actually find all the dimensions here. So the first thing I want to point out is that since this is the leash of Moo the whale, that entire length from here to here is going to be 100 yards. That was given to us. Works out really nicely. The second piece I want to label is I want to at least draw in, and in fact I might make this I'm going to make this a straight line. What the heck? The next thing I want to do is I want to draw that straight line to establish the end of our rectangle there. There we go. I want to establish that line so that we can really talk about the rectangle that's happening as well. So there's that. I'm going to change the color of this piece in just a second as well. So that and that, let's make them both purple. So there's that piece. So we're going to actually find the dimensions of the rectangle. After we do all that, then we will deal with the segment itself, the segment of the circle, or the segment in this picture. So now that we have that, let's label a couple other things, because a few of these pieces are given to us. So the first thing is they did tell us that the radius of the semicircle was 20 yards. So that means that this length is going to be 20, again in yards. And likewise, although we didn't mention in the very beginning when we started the problem, this length, oops, I went a little bit too far there, my apologies. This length is going to be 20 plus 20 is 40. Think about it, there's two radii that are here. One that's 20 right there and one that's 20 right there. So we're able to get our 40 length right there. Finally, we will want to find the dimensions of this rectangle, but it is important to note that we do have one dimension of the rectangle. It's 40. So we just have to find the rest. So from here, if we wanted to begin, I will say that we could automatically find the area of the semicircle. I'm going to say area of semicircle. So our area of that semicircle is going to be, pretty simply, half of the area of the entire circle with that radius. So it's going to be 1/2 of pi times 20 squared, also known as 200 pi. So pretty straightforward to find, but there is the area of the semicircle on the left. So that's completely taken care of. That does, though, mean that our next move is going to be figuring out the area of the rectangle that we have here. Let's see if we can get that thing set up. So there's our first piece. There's our second piece, at least labeled. So we need to figure out the length of that pink section. That's really the challenge that we have going on here. So let's think about what situations we have that'll let us find it. So what I want to point out, and again, I'm going to erase this afterwards just to kind of see it, but we actually have defined a right triangle in our diagram. There's a right triangle, well, right there. So what I want to do is I want to label this, and I want to start to think about some of the dimensions here. Well, first, we know the hypotenuse is 100 because that's the length of Mumu's leash. But second, we also know this height of that triangle, which is 20, because that height is the same as the radius of the far left semicircle. So we actually have that information as well. And what that does is it means we can use the Pythagorean theorem to find the third side. Basically, if we want to know how long this section is, we just need to use a squared plus b squared equals c squared. So up there, that would mean 20 squared plus the other thing squared is going to be equal to 100 squared. And now as I go to calculate these pieces, I mean, first of all, I should probably change the color so that it doesn't match what I just did at the semicircle. So I'll start there. But second, as I go to do this, I'm trying to figure out what that length is. So I'm just calling a question mark for now. It's going to be 100 squared minus 20 squared. And you might think this is an odd way to do it, but I'm trying to keep things exact and not use my calculator till the very end. It's just a personal choice. I'm going to factor out a GCF of 20 squared. That will leave me with 5 squared minus 1, or 1 squared. I guess I'll keep it up there. And if we think about what this amounts to, we'll have 20 squared times 24. So our length is our length squared is 20 squared times 24. If we want to solve for the actual length of that section, that length will be 20 times the square root of 24, which is root 4 times 6, otherwise known as 2 root 6. So we can go ahead and say that that length is going to be 40 root 6 yards. So it's really helpful and essential using this approach to figure out that dimension. So that entire dimension there is going to be 40 root 6. Now going back to our rectangle for a second, we actually now have enough information to figure out the area of the rectangle and get our second little geometric shape fully out of the picture. The reason why we can do that is that we now know that the entire, we'll call this kind of bluish purple line there, the height of that triangle on its side is 40 root 6, and we know that this length right here, from there to there, is 20, because that's just the radius of the circle. And the reason that helps us is if we want to label the dimension of that particular side of the rectangle, right up here, it's going to be the full 40 root 6 minus the radius length, which is 20. So there is the length of our rectangle. So based on that, we can also go over to the side, basically collecting pieces here. We can find the area of the rectangle. Of course, this won't finish the problem, but at least it gets us somewhere pretty valuable. The area of that rectangle in the center is going to be the base times the height. Well, the height of that rectangle is the 40 that we were given by the information about the semicircle. The height, on the other hand, is 40 root 6 minus 20. And if you wanted to multiply this out, for some reason I did yesterday, I just kind of felt like it was cool to do it, you get 1600 root 6 minus 800. So congratulations, everybody. We've found 2 of our 3. So it's basically everything here is gone, everything in here is gone. We are left with this tiny little thing. That's all that's left for us to actually find. So that's what we have left. How do we find the area of that piece that's called a segment? And this is where I want to say the best geometry is going to pop in here. So let's go take a look at that piece particular, and we'll come back and grab those pieces. So here is our piece. We are focusing on trying to find the area of this section right here. We want to find the little area right there, what's called the segment of the circle. And to do that, we're going to use a lot of different little pieces. So to help us with it, I'm going to redraw it, and I'm going to exaggerate it a little bit. Forgive me for kind of dropping the scale. I just think it's a little easier to see if we draw it out a little bit more cleanly. So although it's not a huge section, this is just like taking a slice out of a circle. So in fact, I've drawn it here. It almost looks like an ice cream cone. But in a sense, it's the same thing as taking an entire circle. That wasn't bad for freehand. And saying we want to find the area of a single slice right here. This thing would be what we call a sector. So that's what we're trying to find the area of. In this case, though, if we want to do that, we need to sort of compare the sector to the entire circle. And in fact, we want to keep in mind that it's a proportion of the circle. Like one slice is one fraction of the circle, and we can find that fraction of the circle by using both the angle as well as the radius, like the dimensions themselves. So here's what I mean. If over here we had a circle with radius r, and we had a sector with angle theta, and I am going to put theta in degrees here. The only reason for that is that some of the students in Mathletes today haven't yet learned radians in any depth, so basically I want to keep it in degrees so it's a little more approachable. Of course, when I did this problem originally, I did use radians, but teach their own. So what I want to point out about this particular case is if we want to figure out the area of the sector, we can think of that area as being a proportion of the entire circle's area. So that's exactly what we're going to set up. The area of the sector divided by the area of the circle, which in other words is a proportion. Obviously this is a number less than or equal to 1. Well, that's going to be proportional to or equal to the ratio of the angle theta over the entire number of degrees in a circle, which is 360 degrees. And based on this information, since we know the area of this circle is going to be pi r squared, just looking at it, we know the radius is r, and circles have area pi r squared, we can actually multiply this stuff over and get that the area of the sector is going to be equal to theta over 360 times pi r squared. I think this might be getting close to the bottom, so let me just adjust this really briefly. So basically there's what we got. We have this as sort of our area of a sector formula. And we're going to use that exact thing over here in our picture. So let's try to translate it. Again, we can't see the gigantic circle that's here. We just can't see all of it. Kind of looks like an eyeball, actually. It's kind of creepy. Let's go back to Desmos. We can't see the entire circle, but at the same time, we can actually sort of see what's happening here. If I drop the restrictions for a second, notice that it is part of a circle. Like that is, in fact, what's happening there. So basically, we want to figure out like what is the entire area of that circle, what fraction of the circle is there, what's the angle that we're seeing, and then we can actually work our way through. So let's go ahead and translate some things in here. So first of all, I said I wanted to redraw this sector over on the side. That's exactly what I did. So I'm going to first draw it. So it's been rotated. So bear with me, we're rotating these things. I'll label both of them. We said that since the leash of Moo the whale is 100, that means the radius of this circle that we're looking at, a small sector of, is 100. And then we don't know what this angle theta is, so we're going to have to actually figure out what theta is in degrees. But I can point out that this side will be theta in degrees, and so will this side. So we have two different pieces with the angle theta. And we're going to use one at a time, and then we'll deal with the rest of this. And now, of course, we are trying to find the area of just this top part, but for the moment, we're going to set that aside. We will deal with that in just a moment, but for now, let's just find the area of the sector, and then we'll play from there. This is true in whichever method you happen to use, by the way. You'd be using the sector. So in looking at this piece, the real question becomes, how do we find the angle theta? Because we need theta so that we can figure out a proportion. Like what proportion of the circle are we actually seeing in Moo tank? And so in order to find that, we can look back at our labeling for the original triangle in there. So we said that based on the measurements that we were given, the height of this right triangle is going to be 20. And then based on the work we did on the previous page, this horizontal length is 40 root 6. If memory serves, yeah, 40 root 6. So given that, we actually have enough information to figure out theta by using just straight up trigonometry. If we want to find theta, we can point out that the sine of theta is going to be equal to opposite over hypotenuse. Opposite over hypotenuse simplifies to 1/5. And if sine of theta is 1/5, that's the same thing as saying that theta is equal to sine inverse of 1/5. So this is our angle. Now, of course, if we had this thing in degrees, I think we can do that really quickly here. if we wanted to know what that theta angle is equal to, oops, theta would be equal to arc sine of 1/5. Now, of course, the answer, oh, sorry, we got to give it that way. Arc sine of 1/5 is given in radians, so if we want to convert this to degrees, we'd go times 180 over pi. So if you're looking for it, it's about 11.537 degrees. So there it is in degrees. But we don't actually need to think about it. I'm just going to leave it as sine inverse of 1/5. As I said, I like to keep things exact as long as possible so I don't make rounding errors in the intermediate piece. So that's going to be our angle theta that we needed right here. We know 360 degrees gives the full thing, and we know the radius of this circle, the circle that we're seeing a sector of. So in fact, we're actually ready to figure out the area of that entire sector. The area of this sector that we are looking for is going to be equal to some fraction of the entire circle. It's going to be the fraction sine inverse of 1/5, or so you'd think. Give it a second, we'll get there. There's something wrong, but we'll catch it. Sine inverse of 1/5 over 360. And of course, we're in degrees, so I'll go ahead and mark that degree symbol there. And then times the area of that circle, and that circle has radius length 100. Now this feels like it's right, and in fact, the second time I did this problem at school this morning, this is what I got. This is conceptually pretty close to correct. There is just a problem that's built in here, and I don't mean the whole whale part. Oh no, I can't get it to highlight. Okay, I'm going to draw that again. There is a problem here. The problem we have is that we wanted the angle of the entire sector, but we only covered one side of that sector. So in fact, if we want to do this correctly, we need to cover both the left side and the right side. In other words, we need the theta that's here as well as the theta here, because there's two different equal thetas that combine to give us the entire angle for that sector. So in fact, I need an extra 2 right there in order for this to be correct. So when I put all that in and make that adjustment, we're going to see some simple things here. We have 2 over 360, so that's going to be sine inverse of 1/5. Again, I like to simplify. I feel like it's nice to have everything as clean as possible. Oops, that should be 180. So sine inverse of 1/5 over 180 degrees, and this is all times pi times 100 squared. So that's 1, 2, 3, 4 pi. If we want to simplify it a little further, we can. So based on that, is that 1,000 pi? We're going to get that this area is, well, 1,000 pi over 18. That can be 500 pi over 9. We're going to get 500 pi over 9 times sine inverse of 1/5. Now, before you go run and start adding this to our previous answer, this is not actually what we were looking for. Sorry to break the bad news to you. It's not. This is the area of the entire sector. And we only want the area of the section that's right above it. So we only want this section. That's the only part we're missing in our picture. We have everything else already. We've got all the rest of Mumu's access area. So in order to find that, what we need to do is take the area of the sector that we just found, and we need to subtract the area of the triangle, because the triangle is the only difference between the segment we want and the sector that we found. So in order to do that, we just need to subtract away the area of this triangle. Fortunately for us, we can subtract away the area of the triangle pretty easily. So the area of the triangle is 1/2 base times height. We just need to figure out those dimensions. So we are going to subtract off 1/2 base times height. The base of our triangle, I mean, it's a little awkward here. The base is vertical, but I'm going to go with it. The base is 20 plus 20 is 40. And the height of this triangle, again, it's on its side, but that height is going to be 40 root 6. And when we combine those two things together, we're going to end up with, it looks like 500 pi over 9 sine inverse of 1/5, whatever that is in degrees. And again, we did keep everything in degrees here. On this side, 40 times 40 is 1,600, but we're cutting it in half. We're going to have minus 800 root 6. And this, after all of that work, this is the area of that tiny little segment that we were looking for. It's that little chunk that stretches beyond the rectangle. That was sort of the missing piece that we have. Based on this, we are ready to actually finish this problem. So let me get that set up and then we'll pull it up here. Okay, we've got all our information collected here. We're ready to find both the area that is accessible to Mumu the whale, and then we're also able to find our percentage answer. So let's do both those things here as we go. And we do have to keep in mind as we do it that we are in degree mode. So we are like a college-going student with ambition. We are in degree mode. So with that said, let's set this up. So first of all, the question that we had first was what area was accessible to Moo the whale. So the area that Moo can reach, I'm going to call it the area of Moo, but obviously we're not measuring the surface area of the whale, we're measuring the area he can reach, is going to be the combination of all those pieces. It'll be the semicircles area added to the area of the rectangle, which was at 1600 root 6 minus 800. And then finally, we have to add to that the little segments area, which in fact, I'm going to go ahead and be just a tad lazy. Forgive me. I'm going to just throw that in there. So this is the area that Moo can access. And we have the decimal value for that. This is going to be equal to, and we'll keep it exact here so that we make sure that we get it correct. This is going to be equal to, again, keeping things in degree mode, it appears that this is going to be equal to 3,801.48953 ... So there's our first piece. That's the area that Moo can access. Now the second thing we need, of course, is what is the area of the entire tank? We do need to make sure that we have that. So area of the entire tank. Now we've sort of taken this for granted, but looking up there in our picture, we can see that it's comprised of three pieces. Two equal semicircles, or two congruent semicircles, and a rectangle. Now I'm going to go ahead and point out, I think this is probably a given after all the other difficult geometry we've done, that those two semicircles are going to add up to a full circle. They have radius 20, so basically that area will combine into pi times 20 squared, or 400 pi. And then second, we have a rectangle's worth of area, and that rectangle is width 300 and height 40 from the 220 unit radii. And if we combine those two pieces together, we'll have 400 pi plus it looks like 12,000. So there is the area of Moo, the area of the tank. What we want to figure out is, of course, the percentage. So the percentage that we're looking for is going to be, and we want to write it as a rounded to the nearest percent, so we'll do this as a decimal first, and then we'll just make the conversion. That percent is going to be the ratio of two things, as you know. It's going to be the area that Moo can access, so the area that we found earlier, that 3,801, and then it's going to be divided by the area of the entire tank. And then we can check to see whether this is within regulation, which I doubt it is, but who knows. So when we combine those two things together and divide, I have the decimal here, this is going to turn out to be exactly 0.8 or 28676. And in terms of this, if we want to get this as a percentage, like actually written out that way, this would be 28.676, and I'll put dots there, percent. But we were supposed to round it to the nearest whole percent. So that tells us that in this tank, with the leash, with that ridiculous leash tied to a whale, Moo the whale can only access about 29% of the tank when leashed to the point that he is with that 100 yard long leash. So our correct answer is 29% after all that. So having said that, tough problem. But what I love about this problem is that it brings together a bunch of different geometric ideas all together, and that there's some sort of difficult intuition here to kind of think about. We've got to think about how that leash stretches, and like what areas are accessible, and can Moo actually access pieces here, and which structure, which breakdown of our region, where were we? This section, which breakdown should we use? Maybe you wanted to really use that sector instead. Heck, in my approach, we even figured out what a segment was. So we got to do a lot of really good stuff here, a lot of really good math. And as I said before, this problem was inspired by one of our greatest members, Eric. And so I wanted to, of course, wish Eric happy birthday as well in case he happens to watch this video. But for us, you were probably tuning in for the percentage itself, and you maybe even fast-forwarded to the end. Should have put some sort of fake answer at the end. But 29% was our correct answer. If you're looking for sort of other problems along this line or other ways to think, question I wanted to ask myself was how wide would the tank need to be? Sort of like, what would this length need to be for Moo the whale to be able to reach exactly 42% of the tank? That was one of the questions that I considered asking until I realized how difficult this was. The other one would be to figure out, like, what is the maximum length that, or what is the minimum length that Moo the whale could have, or where could you tie it so that he could reach a certain amount? There's lots of really interesting questions that are built in here. If you're a person like me who has an affection for leashing mammals to things and trying to see how far they can stray from their point of attachment. But for us, I just wanted to kind of run through this problem and present a solution just in case you were still curious. So without further ado, I'm going to call that a night and go to bed. This is my bedtime or past my bedtime. Whether you're a member of our Mathletes team, whether you're someone that just happens to wander onto this video, or you're Eric himself, thanks for watching. Hopefully you got something good out of this as you watched it, and have a great night.